All right, let's now take a look at a concept called centripetal force. So in the last video, we learned about centripetal acceleration. So now let's talk about centripetal force. And we're going to start by looking at, hey, look at this guy. Who is this? This guy looks familiar. This is me, actually. And I am in the rotunda, and I am spinning two rubber spheres around my head. So,
I'll tell you when to stop.
So as I'm doing this, I'm going to refer back to this video. I want you to notice there's a string attached to both balls as they spin around my head. And I'm pulling down on the string, and it takes a considerable amount of effort for me to pull the string down as the balls are spinning around. And so I'm going to use this video kind of as a jumping off point to talk about some terms here. So the first term is, in fact, centripetal force. And centripetal force is a topic that can be one of the more trickier ones in physics. The textbook definition is centripetal force is the net force on an object that's doing what's called uniform circular motion. So uniform circular motion, this concept, means that an object is going in a circle at a constant speed. Now notice I didn't say constant direction, because we know as an object goes in a circle, its direction is changing, which is why we say that it has a centripetal acceleration. Now, what causes a centripetal acceleration? Well, for the ball going in the circle, what we see here, and this is really cool, it's the string itself that provides the centripetal force, right? The gravity of the ball is acting down, but that's not towards the center of the circle. The only force is the x component of the string's tension, and so that force is what's in the what's causing the ball to go in the circle. Which, of course, I felt that in the string. I felt that tension when I pulled down on the string. I could feel that force in that string, and that's the centripetal force of the string. For different rotating situations, the centripetal force is different. Take, for example, let's go back to our Larry the Bug here. Now we look at Larry the Bug. Right? As Larry's rotating, what is causing the centripetal force? Well, if you said the friction between Larry and the turntable, you would be correct. You can imagine if this were all ice and there were no friction, he would slide right off. There would be no centripetal force, and therefore he would not be able to go in the circle. But since there is friction, it allows him to go in a circle. An extreme example of the use of friction to allow objects to go in a circle is NASCAR. For a race car going in a circle around the track, the centripetal force is supplied by the friction between the car's tires and the road. And so, because the cars are going at such a high speed, imagine if the road surface were ice, the cars would slide right off the circle. And so the friction is the inward force that allows them to continue to go in the circle. So it's the centripetal force. The reason race car tracks are banked are because these cars are going at such high speeds that if the road were flat, there wouldn't be enough friction. So they bank the road to increase the amount of friction, increasing the amount of centripetal force. And we can see this here. Different race car tracks, like Martinsville, has only a 12-degree angle versus Talladega, which has a 33-degree angle. So let me ask you, at which racetrack can a car go faster going around the turn? Well, if you said Talladega, you're right. And the reason is because it's a greater banked surface. The car can go faster and still stay on the track than it could at Martinsville because there's more friction available for the car. So I've got a short video here to kind of show you what's going on when a car goes around these turns in a NASCAR race. All right, one more way I want to illustrate centripetal force to you is I want to show you another situation and to see if you can identify the centripetal force. Here we have one of these embroidery rings, which I had a successful or maybe not so successful demo earlier in the year with inertia trying to remove chalk or removing the ring. I pulled the ring this way and the chalk fell down. Here what we're going to do is we're just going to have a ball rolling around the ring, and I want to ask you two questions. The first question is, what provides the centripetal force to keep the ball going in the circle? And the second question is, if the circle's removed as the ball is going around, so let's say the ball is here, and the circle's removed. So the ball's going this way, and you remove the circle, what direction will the ball go? I guess some of your options would be, if the ball is here, it could just keep going in the circle like that. It could go straight. It could go down like that. Okay, so that's kind of what I want you to think about. Which direction will the ball go when the circle, the ring, is removed? All right. Also, one other thing. There is no force called centrifugal. Centrifugal force is an outward force, and I'll talk about why this is a fictional force in a second, but this centripetal force is an actual force, and we'll see it at play here. So let's watch the video. And we'll see once he gets the ball going. Okay, I'll pause it here for a second. Okay, as it comes around, he's going to let the ring go at this point. I want you to watch which direction the ball goes and see if it matches your prediction. And also, what's providing the centripetal force? Well, the ring at all times is pushing in on the ball. And so it's the force of the ring pushing in on the ball that keeps the ball going in the circle. So if you said the ring, pat yourself on the back. Nice job. That is correct. And here we go. Let's watch what happens when the ring is removed. Okay, if you didn't see that, we'll watch that again. You see the ring is removed here as the ball is traveling in this direction, and we should see that the ball continues going in a straight line tangent to the circle. Rewind that one more time so you can see that again. We can see the ball in the ring here. The ball was going in this direction around the ring, and it just continues going in a straight line. You can ask yourself, why is that? What is it about the ball that makes it just continue to go in the straight line path when the circle's removed? Why doesn't it keep going in the circle? Well, the reason it doesn't keep going in the circle, right, is because there's nothing to cause it to go in the circle anymore. There's no longer a centripetal force acting on the ball. And so since there's no longer a centripetal force, the ball will no longer go in the circle. Well, why does it go in a straight line? Well, it was already going in a straight line, and we removed the force. So the ball has, if you think back to Newton's laws, what's the I word? The ball has inertia. And so its tendency is to just keep going the direction it's going, which at that point in the circle happened to be in that direction. So the ball just keeps moving in that direction. That is an awesome, awesome thing that we just saw there. Something that's not many people understand. Hopefully you grasp that, or by the end of the video you will, that when the force is removed, the centripetal force is removed, an object will just go in a straight line. It's kind of cool. So you might ask yourself, what is the centrifugal force? Well, for the example we just saw, remember, as I swing the ball around my head, I supply the centripetal force. This force acts on the ball, right? And that's the force that keeps the ball going in this direction. The blue force actually isn't acting on the ball. Centrifugal force acts on me. It's the force on me, which is a result of my force on the ball, right? Newton's third law. What does it say? For every action, my force on the ball, there's an equal reaction. The ball's force on me. But I feel the centrifugal force, which is why we think it's the force that causes the ball to go in the circle. But it's not. It's the reaction force. And here we see the path of inertia. If the ball were going in this circle and someone were to cut the string, the ball would continue to go in this direction. Newton's never wrong. Now this video has been all about concepts. Just to understand the concepts of centripetal force, But I will show you the math part of it as well. If you remember centripetal acceleration, right? Centripetal acceleration is Vt squared, the tangential velocity squared over the radius of the circle. Now, that's acceleration, but Newton's second law says the net force in an object is equal to m times the acceleration. So guess what the equation for centripetal force is? I just take my v squared over r, which is my acceleration, and I multiply it by mass. Again, Newton's laws rear their heads, and this time in a very helpful way. And this we'll do in a practice problem in the next video.